Automated guided vehicles, or AGVs, are a staple of industrial logistics, but they come with a severe operational limit. They rely entirely on fixed physical infrastructure to navigate, usually painted floor lines or magnetic wires. If a dropped box blocks that line, the machine stops dead in its tracks, unable to deviate from its hard-coded path. An autonomous mobile robot, or AMR, solves this by operating independently of floor markings. It uses onboard sensors to constantly scan its surroundings, dynamically mapping a new route around that same dropped box on the fly. Mapping a room is only one layer of the problem. To achieve complete robotic autonomy, the system must eventually sever its reliance on all external signals, including GPS and radio connections. Absolute physical independence is a strict requirement for machines operating in environments where external signals either fail completely or take too long to arrive. Deep underground mines, underwater trenches, and the surface of Mars all require a machine to navigate without calling home. True autonomy is the ability to continuously answer two questions: where am I, and how do I get there, using only hardware contained entirely within a closed system. Engineering this independence requires solving two distinct mathematical problems. The first is state estimation, which is the continuous calculation of the robot's exact internal coordinates and orientation at any given millisecond. The second is kinematic control. Once the robot calculates exactly where it is, kinematic control provides the physical, mathematical instructions required to drive the hardware to its final goal. The foundational hardware that makes exact state estimation possible without external signals is the Inertial Navigation System, or INS. Originally developed to guide early aerospace programs like the Lockheed F-104 starfighter, this technology operates strictly on the physical laws of motion. To navigate autonomously, engineers must first isolate pure inertial physics from the universe's forces to build a pristine state estimate, and then translate that raw data into mathematically constrained control systems. The INS uses a concept known as modern dead reckoning. Instead of checking a satellite, the system calculates its exact location by continuously measuring its own physical inertia as it moves. Inside the INS, accelerometers measure linear acceleration along the x, y, and z axes. Integrating that acceleration calculates exact velocity. Performing a second integral extracts precise physical position, revealing exactly how far you've traveled from your starting point. But this pure math collides with a severe physical flaw. An accelerometer measures physical force, meaning it cannot distinguish between the forward thrust of a vehicle and the constant downward pull of Earth's gravity. Imagine a vehicle driving forward, pitching onto a steep incline and stopping. Because the accelerometer tilts, the downward gravity vector bleeds into the horizontal x-axis. Though stationary, the system registers gravity as forward acceleration, calculating velocity and position that accelerate toward infinity. Unless a navigation system can perfectly isolate its sensors and ignore gravity, internal state estimation becomes mathematically useless within seconds. The solution to this tilting problem is mechanical. Engineers take the accelerometers and mount them on a moving platform, suspended inside 3 rotating gimbals. 2 gyroscopes are attached to this platform. Spinning gyroscopes naturally resist changes to their orientation. Their inertia holds the center platform perfectly level, mechanically isolating the accelerometers, no matter how violently the vehicle pitches or rolls around them. But fixing the platform to a static point in space creates a new complication. The Earth is a rotating sphere. If a gyroscope holds its orientation perfectly fixed, it eventually misaligns with the local horizon as the vehicle travels across the curved planet. If an aircraft flies from the equator to the North Pole, a fixed platform appears to tilt backwards by 90 degrees from the perspective of the pilot, once again exposing the accelerometers to gravity. In this closed-loop feedback system, accelerometers feed real-time position data into an onboard computer. The computer calculates how much the Earth has rotated beneath the vehicle, then uses motors to torque the gyroscopes by that exact amount, constantly re-leveling the platform. This continuous high-speed conversation between the linear accelerometers and the angular gyroscopes generates a pristine, self-contained state vector, giving the vehicle its x-coordinate, y-coordinate, and heading angle. We now have perfect internal data telling us exactly where we are in 3-dimensional space. The next step is physically driving the hardware to a destination. To understand how autonomous motion is programmed, we look to the car-like mobile robot, which serves as one of the most common structural platforms in commercial automation. The mathematical limits of any robot are defined by its mobility, which is the strict number of independent motions the hardware can physically execute. A car-like robot is subject to a non-holonomic constraint. Because its rear wheels are fixed in their alignment, the vehicle is physically restricted from sliding directly sideways. We map position x and y, heading theta, steering phi, and wheelbase L. Change in x is velocity times cosine theta. Change in y is velocity times sine theta. Rotation rate is velocity divided by wheelbase times tangent phi. Programming autonomous motion involves solving a continuous matrix of physical constraints, moving beyond simple geometric plotting. Getting a robot to reach a set of GPS coordinates is called moving to a point. Practical automation requires executing a far more demanding task, moving to a pose. Reaching a pose mandates that the robot arrives at a specific XY coordinate while simultaneously locking into a precise final orientation. When an autonomous warehouse robot needs to recharge, simply driving near the station isn't enough. It must approach the target, calculate its turning radius, and slide flawlessly backwards into a narrow wall-mounted dock. This diagram shows the computer's calculations. It measures 3 errors: position, rho, current heading, alpha, and final orientation, beta. A PID controller pulls live inertial navigation data, analyzing these metrics to continuously update velocity and steering, forcing all 3 values perfectly to 0. Achieving a perfect pose represents the complete harmonization of the machine. The internal sensors generate pristine physical data, and the kinematic math translates that data into precise mechanical execution. Despite the mechanical strength of the INS and its feedback loops, physics exacts a toll. Over long durations, the double integration process will inevitably accumulate microscopic noise into measurable location drift. To combat this, modern systems utilize sensor fusion. The autonomous vehicle relies completely on the lightning-fast, self-contained physics of the INS to handle immediate kinematic control, but periodically references external sensors like LiDAR and cameras to truth-check and snap that internal data back to reality. Robust autonomy is a synthesis of internal physical isolation and external digital verification.